is a light switch. Yes, the same light switch we use to turn on and off lights in our homes. I'm sure at this point you're asking, what does this have to do with how computers work? Well, surprisingly, quite a bit. This video will examine how the fundamental building block of a computer resembles a switch, what operations the brain of a computer, the central processing unit, or CPU, does with these building blocks, and we'll demystify the magic trick behind why computers help us in so many tasks. Okay, back to the light switch. The light switch controls if an electrical connection is made to the light bulb in this example. Either the switch is on, connecting the electrical signal to the light bulb, which illuminates the bulb, or off, preventing the connection from being made. Surprisingly, a transistor, which is the fundamental building block of a computer, follows similar properties under a simple model. The main difference being the transistor is switching on and off by an electrical signal instead of how we physically use a finger to control the light switch. And while transistors are able to behave in more complex manners, the simple switch model of transistor operation serves as a great mental model for what is going on inside of a computer. In fact, I would estimate that 95% of people will never need to know a more in-depth model of transistor functionality. However, our light switches at home cannot play this YouTube video. So how do we create the ability to perform the complex and important tasks we ask our computers to do? Well, we can combine multiple switches together to form logical functions. For example, let's put two switches connected, one after another. Now, if we only turn on a single switch, the electrical circuit connection with the light bulb is not formed. In order to turn on the light bulb, we must turn on switch 1 and switch 2. We will refer to this as the AND function, since switch 1 and switch 2 have to be closed for the light bulb to be illuminated. Alternatively, the switches could be connected in a parallel fashion, meaning that the output of switch 1 and switch 2 both connect directly to the light. In this case, simply turning on one of the two switches does create an electrical connection, and is able to turn on the light bulb. Now, the only case that causes the light bulb to be off is when both switches are not connected. We will refer to this functionality as the OR function, since only switch 1 or switch 2 have to be on for the light bulb to turn on. While it does not seem like these simple logic functions could serve as the underlying logic for a computer, these types of logic functions really do allow for the vast majority of computer functionality. In actuality, we would only need one more logical function to make the logic of a computer. Until now, we were inherently assuming that the switch was being turned on by a logic 1 signal, or finger pressing the physical switch if that is easier to visualize. We need a function that turns the switch on when a logic 0 or no finger is being applied to the switch. This type of logical function is called a NOT, or an inverter, since the output is the inverted signal of the input, i.e., the output is on when the input is off, and vice versa. I do not want to spend too much time on the details of the specific logic and how to implement it in this video, but want to reiterate that simple logical functions can be created from the switch-like operation of a transistor. And quite amazingly, using enough of these small logic functions, such as AND and OR functions, we can form more complex functionality. Modern CPUs, or the brain of a computer, can have millions of these small functions to allow for the functionality we utilize computers for. While this is very interesting in its own right, the next logical question becomes, what type of operations do we need out of these small logical functions to enable all of the applications we do with our computers today? The answer to this question may surprise you. It certainly surprised me when I learned it. The first type of functionality needed is the ability to act like a shipping and receiving center. To visualize this, let's picture the CPU as your house, and you need the ability to send items to a storage unit and get items from the storage unit. The main difference between computers and humans is that computers are not storing childhood bowling trophies. Instead, they store electrical potential in the forms of voltages, which is a lot of technical jargon that we will not cover in this video. All you need to know now is that there are two different voltage states for each object, which we can visualize as a light bulb being on or off. Another common way of abstracting the voltages, which you may have heard of, is to use ones and zeros. This maps well to our light bulb visualization, where a 1 is a light bulb that is on, and a 0 is a light bulb that is off. The state of a single light bulb then represents the smallest unit of information in a computer, a bit. To act like a shipping and receiving center, we need to load, store boxes of bits of information, light bulbs in on or off states, between the CPU and the storage unit, memory. Looking first at a load operation, we can think of it as getting a box of light bulbs, some on, some off, from the storage facility and bringing it home, which provides it to the brains of the computer in our example. The positions of what light bulbs are on in the box tells us about the value that was loaded. I will leave out how to decode the values from the on-off positions until another video. A store instruction will do the opposite, taking a box of information, states of light bulbs, saved in the CPU, which is our house, and delivering it to the storage facility until they are needed again. The ability to load, store information is great, but being able to perform an operation on that data is crucial. The next category of instructions we need is arithmetic, or being able to manipulate the values provided to the CPU. Surprisingly, the arithmetic operations used in computers are mostly taught in elementary school, like addition, subtraction, multiplication, and division. The applications we run on our computers, even watching this video right now, are largely composed of these load and store and arithmetic instructions, which always seemed impossible to me when I first learned about it. But I promise you that within the past second of watching this video, your computer has loaded two values from storage, added them together, and saved that result. There is one other type of operation that is required in addition to the load, store, and arithmetic operations we discussed so far. We also need the ability to decide what to do next based on a provided piece of information. The parallel to our daily lives would be conditional decisions, like, am I hungry? If so, then eat. Is it raining? If so, then bring a rain jacket. So on and so forth. We will refer to this type of conditional instruction done by a computer as a jump. The name jump in a way mimics the use, since we either stay doing the current operation or jump to another operation when a condition is met. For example, if I am hungry, I jump to eating. Otherwise, I continue doing what I was doing. And that's it. To recap the types of operations a computer does, we had loading and storing information, elementary school arithmetic, and the ability to jump around what instruction is executed next. I'm guessing that you are in disbelief that such a simple set of instructions can allow computers to do what they do. Questions like, how does my screen update from addition and loading and storing? How does the computer get a mouse input? So on and so forth, are all very good questions. While we won't talk about how the peripherals we connect to a computer work in this video, a series of loads, stores, arithmetics, and jumps really do allow us to send or receive the information necessary to interface with a screen or mouse. There is one major magic trick that computers do behind the scenes that helps with understanding why these simple operations are able to create the illusion of complex functionality. In magic, there is a concept known as sleight of hand, which can rely on timing or misdirection to create an illusion. I believe computers use sleight of hand to create the illusion of performing very complex operations, whereas we saw that only a handful of simple operations dominate computer programs. The sleight of hand or illusion of a computer is the speed at which a computer performs those operations. A typical computer is running operations at over 1 gigahertz, which can roughly be equated to performing 1 billion operations in a second. That speed is how we can take the simple operation of a switch, create simple instructions with those switches, and utilize those simple instructions to make all of those computer programs we rely on today. So the one-sentence summary of how computers work is that they perform stupid simple operations, but they do those operations stupid fast. Hopefully this makes you appreciate computers in a way you did not previously, and also makes you realize that the skill set needed to design and build computers may not be as complex as you previously thought, once we break it down into the fundamental components. If you are interested in breaking down complex ideas into the fundamental components, please subscribe to this channel and make sure to share this video with others you know who have a curious mindset. Make sure to comment down below with what your curiosities are for future video topics. Oh, and to the first person that spots the hidden video, I'll let you know where you can find your prize.